Okay, so sorry for that. So yeah, so I will go through some methods, but also some concepts to study collective brain dynamics. So the first step, I will show some ways to describe the state of the collective activity and how this state can change and link it to phase transitions. And then in a second part, I will show how the activity can scale as a function of coarse graining. And at the end, I will talk about some non-stationary, non-equilibrium dynamics, such as neuronal avalanches. So, okay, so let's first say that you have a system that can produce binary activity, for example, spiking activity, but also neuroimaging that you threshold and you convert into binary activity, assigning zeros and one or -1 and 1. And let's say that your task is to describe these vectors of activity that are binary patterns of n dimension, where n is the number of channels, neurons if it's spiking activity. And the question is, I want to know what is the probability distribution of all possible binary patterns. So because these are binary patterns, you have 2 to the n patterns. And so when n is large, not even so large, like when n is equal to 40, for example, you have more patterns than stars in the Milky Way. So you cannot do simple histograms to compute the distribution you are looking for. So you need a model. But here the point is that, okay, you are not totally blind when you want to construct a model for your probability distribution. You know some things from the data. For example, you know the mean activity of any of the channels. You know, you can calculate also with a good accuracy the pairwise correlations, for example. And so you have different statistics that you can compute with high accuracy. And so now you're looking for a probability distribution that is also compatible with these observations. Okay. So let's say that we're looking for a probability distribution that matches some expectations on some observables. These observables can be the activation rates or the pairwise correlations. And so you have different statistics that you would like to match. And so the idea is that what is observing the data that you can compute with the n observations, little n observations of your data. So this estimate of the observation has to be matched with what is given by the probability density that you are estimating. Okay. So the model has to match what is in the data. So this gives you some constraints on the probability that you are looking for. So many different probability densities could match with these constraints, but we are looking for the probability density that is the smoother possible, that it has less structure, let's say, meaning that it has maximal entropy. And so now you have a classical optimization problem in which you want to maximize a function, in this case the entropy, given some constraints. And this mathematically you can solve it using Lagrange multipliers. And it would be easy to show. It's some few lines of calculation, but I will skip it. When you do the Lagrange multipliers on this problem, what you get is a Boltzmann distribution. So an exponential distribution, and inside you have something that you can relate to negative energy. This energy is simply is related to the observables that you use to constrain the probability density, and omega are the Lagrange multipliers. So these are the parameters of the probability distribution. And z is the partition function, which is just a normalization constant. Okay, so this is a bit abstract, but let's say that you have some data and you think that the most important in your data is the activation rates and the pairwise correlations. You do the Lagrange multipliers, and you end up with a Boltzmann distribution that has this shape, which is a Boltzmann distribution that has the energy of an Ising model, if you are familiar with. So in this case, you have some parameters that are parameterizing the interactions between the spins. So these sigmas are binary variables that can be -1 or 1. And each spin, if you want, has a local field that describes the tendency of these spins to be up or down. Okay. And so at the end, you have like a equivalent Ising model in which you have a network of interacting spins with some interactions given by this matrix J and local excitability or tendency to be up or down in the parameters H. Okay. And I want to stress that this is not, we're not doing an analogy with the Ising model. This is it's more than an analogy. It's really like a mathematical equivalence. You start with a binary system. You said, okay, I'm interested in the activation rates and the pairwise correlations. And with the maximum entropy principle, you end up with a Boltzmann distribution that has the same shape as an Ising model. That is a model for ferromagnets, no? That we probably all known. This model has a phase transition, second order phase transition, in which so you can scale everything. So you can scale the energy by a temperature parameter that controls the disorder in the system. And so if the temperature is large, you have a system that is disordered because it's overwhelmed by the thermal fluctuations. And in a cold system, when the temperature is low, the interactions are dominated. And these interactions, they like to align the spins, so they produce order. And in between, you have a point that is a critical point in which both order and disorder coexist. And you have these nice self-similar patterns in which you have both order and disorder. Okay. Okay, so let's apply this to some data. So this is data from Bashir Haraya in Neurospin in Paris. So these are macaque data in fMRI. And the macaques can be awake or under anesthesia. So to binarize the data, we just impose a threshold. So every time the fluctuation of a channel is lower than a threshold, we put a 1, otherwise we put a 0. And we have as many channels as we have a partition of the brain. And so the idea is that we can construct these maximum entropy models and also study how they behave when we scaled the energy of these models by a parameter that is equivalent to or analogous to a temperature. Okay. So playing with the temperature, it will tell us how the energy levels are distributed. So we know that in a subcritical regime, you have a low level of activity and some few excited states. But most of the time, the system is in the low energy level, okay? And it barely visits the activated states, okay? If you increase the temperature in the supercritical regime, you will have many accessible energy levels, and these energy levels will be like very close to each other, so the system can jump from one to another, making the system very random, okay? And if you are exactly at the critical point, what you get is numerous energy levels that are well separated. So you can imagine that if you want to code some information in the energy levels, you better be at the critical point because you have like many different, like a large repertoire of accessible states, and these states are distinguishable between them. Okay. Okay. So what we did is, okay, we want to quantify how is the dispersion of these energy levels, and for this we use the specific heat that is no more than the variance of the energies. Okay, so the variance will be maximized at the critical point in this case. Okay, so this is the result for the different conditions. So the macaque can be awake or under different anesthetics. So all this is different molecules for anesthesia. And what we observe is that the heat capacity of the model that we learn from the data, it's always maximum for the wake state. Okay, so it has larger variance in the energy levels. Okay, but how do we want to know if this, for example, in particular, is the maximum possible heat capacity? For this, what we did is, our data by construction has temperature equal to 1. Okay, so this is the model that you get from the data. But then you can scale it by changing the temperature. And so all the models that are not t equal 1 are rescaled models of the model that you learn from the data. And that we observe is that for the awake state, every time you rescale the model, the heat capacity drops, meaning that your system is already at the maximum possible heat capacity, like a critical system. Okay, this is not the case for the conditions with anesthesia. So actually, you need to decrease the temperature to reach the maximum heat capacity for these conditions. So if you need to decrease the temperature, it means that your system was supercritical. Okay, so we can say that there is evidence for a phase transition in which the awake state is in a critical state, and the anesthetized state is in a supercritical regime. Okay, with more disconnected behavior, if you want, and more randomness. Okay, so this is just a way to characterize the state of the system. Okay. Okay, so other quantities you can calculate with the model, not apart from the heat capacity. You can calculate the free energy, which is the useful energy. So is the average energy minus the entropy, is the energy that is useful for work of the system, and we observe that it's maximized also in the wake state. Another quantity is the susceptibility, that is how my system will react to external perturbation. So it is the derivative of the population activity here, denoted by K, how it changes when I apply an external field, okay, or external perturbation. Okay, so the free energy, so the change in free energy relates to the work that can be produced by the system, and is maximized in the wake state, consistent with the critical state. And the susceptibility is how my system will react to external field. And this our external stimulus, and this is also maximized in the wake state. Okay. Okay. So all these quantities that are microscopic, they are consistent with critical dynamics in the wake state. Okay. So then, when we construct this kind of models, we always have like a multiple parameters to describe the system, like, for example, this matrix of interactions and these local excitabilities for the neurons. And we would like to know what is the important parameters in the system. So one thing you can do is, like, let's say that you have a multi-parameter system in which you have multiple parameters, and you are able to construct a surface of the likelihood of the model, okay? And you would like to characterize what is the curvature of this surface, meaning that if it's very flat, I can change the parameters in that directions without affecting the behavior of the model. So these parameters that I can change in a flat region are not very sensitive. But if I have a curve that is very stiff, it means that if I change the parameters in that direction, the system will change a lot. It will change the behavior. Okay, so to characterize this curvature, we use the Fisher information matrix, and it's representing the curvature of the log likelihood of the model, and it has this expression that the idea is that if you see this curvature, well, you will have some parameters or some direction in the parameter space in which the log likelihood is not changing a lot. And this we will call it the slopy dimensions. So these are combination of parameters that are not very important. Whereas you have directions in parameter space that are called stiff, that really are changing the network behavior. Okay. And also we can demonstrate that this Fisher information matrix, it relates to how the free energy changes as a function of changing the parameters. Okay, so let's, for the case of these anesthetized and awake macaques, we can associate to each part of the brain a sensitivity of the parameters. So here I'm plotting the stiffness, if you want, of the different regions. Okay, and what we show is that when we go from awake to anesthesia, we change along the direction of the stiff parameters, so the parameters that are important. Okay, so you could go from one state to another in many directions in the parameter space because it's multidimensional. But what we observe is that the system actually is displaced in a particular direction that is given by the stiff parameters. Okay, and also that these parameters are important because if you stimulate the different nodes of the network, the work that you produce by the stimulation it depends on the stiffness of the sensitivity of the brain region that you are stimulating. Okay. Okay. So this was an example of how to derive or how to describe the importance of the different parameters in neuroimaging, but you can do it also using spiking activity. This is activity from auditory cortex of the rat. So as you know, spontaneously the cortex can change from synchronized to desynchronized state, and this oscillation between these two states it's a random process that has been described. And so the idea here is that we have long recordings with many simultaneously recorded neurons, and we have epochs of synchronized states and epochs with desynchronized states. So what we did is we partitioned all the recordings that are several hours in some epochs of 100 seconds. Okay, and for each epoch, we construct a maximum entropy model that will give us some parameters describing the excitabilities and the interaction between the neurons. Okay, and the good thing with this data is that it's spontaneous activity, but once in a while there is an auditory stimulus, and so we have both. We have spontaneous activity and stimulus evoke activity. Okay, so without surprise, the parameters of the model change in time. So this is like the autocorrelation of the parameters of the model, and they change. Okay, so they are changing in time. But there is one thing that is not changing is the Fisher information matrix. So the sensitivity of the parameters remains fairly stable across the few hours of recordings that we have. No? And so if we separate this Fisher information matrix, you can separate it. Well, you can calculate the eigenvalues, and this gives you the parameters that are, or the combination of parameters that are stiff and the ones that are slopy, according to their rank of the eigenvalues. And so if we separate the parameters into stiff and slopy, we can show that the stiff parameters are those that correlate the most with the change of cortical state between synchronized to desynchronized states. Okay. and the correlation of these changes with the slopy parameters is lower. Okay, so we can say that the system is changing state along the stiff dimensions, which makes sense because the system is the activity is qualitatively different in the synchronized and desynchronized state. Okay. Then, if we observe the evoke activity, we can separate the neurons into, we can classify them as slopy or stiff. We see that when we have a stimulus coming here, a line at time 0, the response of the slopy units, well, it can be positive or negative, but in all cases, the response is larger for the slopy units than for the stiff units. So this suggests that the stimulus is making the system evolve in the slopy dimensions, not in the stiff ones. And so this we check for all the rats, and it's the case that in fact when you put the stimulus, the activity is evolving along some directions that are slopy, which makes sense, I think, because if you put the stimulus, you don't want to change the behavior of all the network. You want to transmit the information, but without changing state, for example. You don't want to go from desynchronized to synchronized state. Okay, and then if you calculate the correlation matrix and you do some network measures for the network of correlations, you will see that the neurons, so each point here is a neuron, the neurons that are highly connected and that are highly connected between them that form the core of the network are those that have parameters that are very sensitive. Okay, and the neurons that are in the periphery of the network, that are a bit disconnected from the network, are those that have a slopy parameter. Okay, so as a summary, let's say that you can divide your system into a core and a periphery, and it looks like the changes in the core correspond to changes in the stiff dimension and produce actual cortical states transitions. Okay, and if you stimulate the system will evolve in the slopy dimensions, meaning that you don't change qualitatively the system behavior as a whole, but you are able to transmit information in the periphery. Okay, so this is a way to channel the information to transmit it just in the periphery without affecting the full system. Okay. Okay, so this was a way to describe the state of the system, and now there are many. So we know that many evidence that are compatible with critical dynamics is the fact that we observe in many situations we observe scale invariance. This can be observed in the power spectrum of the neuroimaging data, but also it is well known that neuronal avalanches are scale invariant. This you can observe at the microcircuit state, microcircuit level, using spiking activity, for example, or at more mesoscopic level using MEG, fMRI, or calcium imaging. So what is the consequence of a critical? So a critical system has self-similarity, so scale invariance. It means that if you rescale if you reduce or you ignore the correlated degrees of freedom, you will recover the same statistics. So I will show an example. This is well-known renormalization group theory. So let's say that you have a spin model, and you group neighbor spins, and then you associate to now this super spin. You associate, let's say, the mean activity or the maximum value of the group of spins. Okay, and so when you do this, you coarse grain your model. Okay, and so the idea is that we want to know what is the probability, how you change the probability distribution of all possible patterns when you are in this condition or in a coarse grain situation. Okay, and what is well known is that so, for example, if you are in a subcritical regime and you rescale the system by doing, like, for example, you do like a zoom out, and then it's like doing a coarse graining, you will end up with a temperature that is equivalent to 0 temperature. If you are at the supercritical regime, so above the critical temperature, and you rescale your system, you will have an effective temperature that goes to infinity. But if you are exactly at the critical point, and you rescale your system by doing coarse graining, you retrieve all the time the same statistics. This is because the system is self-similar. Okay. So this kind of fractal activity is well known at the critical state, and it means that the critical point is like a fixed point in the renormalization process. Okay, when you coarse grain, you retrieve the same statistics. Okay, so we want to apply this technique to neuronal data. For this, instead of grouping neighboring spins, what we can do is that we group channels or neurons that are maximally correlated. Okay, and this has been shown by the group of William Bialek, that if you coarse grain in this way, you expect to find some scaling laws, meaning that, for example, the variance of the coarse graining or coarse grain variables. So when you coarse grain, you form groups of first two channels, then 4 channels, then 2 to the k times the coarse graining step channels, and so on and so forth. Okay, and what you observe, what is predicted is that the variance scales as a power law of the size of the cluster. Okay, and also the probability of having all spins in a given state, like, for example, the probability of silence, that if you assume some equilibrium you can relate to the free energy, also scales as a function of the cluster size. Okay, as a power of the cluster size. Okay, and also the eigenvalues of the covariance matrix, you will scale as a power law with also a given exponent mu. Okay. Okay, so we did this for fMRI signals from the HCP, and we verified that we have these scaling laws, and so this is for more than 1,000 subjects. We can calculate the parameter, the power exponents of the variance, the free energy, and the spectrum of the eigenvalues, and we can see that these exponents are highly reproducible. So for each of the human subjects in this case. Okay, and okay, so we have some scaling of the activity as a function of coarse graining that is parameterized by these exponents. And so we would like to know what these exponents mean. And so for this, we took a simple model in which we take the connectome. So the matrix of fibers connecting different regions of the brain. And so in each brain region, we put a spin that can be activated or inactivated, and we connect the spins with this connectome. Okay, and so this system is a system that has a phase transition. And long story short, more details in this article. What we show is that the exponents that you get with this simple model that has a phase transition, so the exponents at the critical point, they match the exponents that we observe in the data. Okay, so it means that this set of exponents are compatible with critical dynamics. Okay, so this was an example of renormalization group. Maybe I will skip this to talk a bit about neuronal avalanches. So we study these are example of non-equilibrium dynamics, in which, for example, this is a spontaneous activity of zebrafish that can be recorded using a light sheet microscopy. So the larva of the zebrafish is transparent. You can encode the calcium indicators in the genes. And so this larva is trapped into a drop of agarose. And otherwise it's living in vivo. And you can record the spontaneous activity of almost all the neurons in the brain simultaneously with cellular resolution. Okay, and so what you can observe here is that you have some events in which some neurons are, some clusters of neurons are activated. Okay, and once in a while you have like almost all the brain that is activated. So you have activity clusters that are small, medium, and very large. Okay, and so we, in collaboration with Herman Sombre at the École Normale Supérieure in Paris, we use this technique, and we wanted to know how this activity relates to critical dynamics. Okay. So the first thing that we did, we defined what we call a neuronal avalanche. In this case, is a cluster of activity of neighboring neurons that are co-active. And so this cluster, in this case, is represented 2D, but you have to imagine it in 3D. So you have a cluster of activity that will grow and then die. Okay. And so the duration of this growth and die is the duration of the neuronal avalanche, and the total number of recruited neurons is the size of the avalanche. Okay. Okay. So we want to compare these avalanches to those that are produced in a system of spins that we know is this random field Ising model, in which it's a 3D network of spins, and the important thing is that the spins, they have different excitability, and this excitability is just taken from Gaussian distribution. And so these H parameters that are the excitability of the spins, they are randomly picked from this distribution. So there is this quench disorder in the system. Okay. And so the idea is that if the spins are connected by intensity coupling J, okay. So J is a ordering force because the interactions like to align the spins, okay. But the heterogeneity wants to scramble this order, okay. So you have a competition between an ordering force given by this disorder or this heterogeneity in the excitability. And so when the heterogeneity is very large, you have independent spins because randomness is dominating. If the couplings are very strong, then your system is ordered, okay? And maybe you have only one avalanche of all spins aligning together. But when you have comparable order and disorder, when there is an equilibrium, you have what we call crackling noise, meaning avalanches of all sizes. Okay. So this is described by power laws. So you have the fact that you have avalanches of all sizes are described by these power laws in the size, in the t now is the duration of the avalanches, and also you have a relation between the average size of an avalanche and the duration. Okay, and so these are power laws with given exponents, and these exponents are precisely equal to some critical exponents in the critical point where you have crackling noise. Okay. Okay, so these are well known. These exponents are those for this random field Ising model, and what we and also these exponents, they are related between each other. This is actually, you can show it with the renormalization group. And what we observe now in the data, so now these color probability densities are from different larvae of the zebrafish. So what you can see is that the probability densities are clearly power law. Most importantly, the exponents that we get from the data, they match the exponents that are predicted by critical system producing crackling noise. Okay, and also these exponents that we observe, they are related as predicted by theory. So this quantity is close to 1 in our case. Okay. Okay. So the question is, how functional are these neuronal avalanches? So for this, what we did is we put the fishes in a bath with eptanol, and eptanol makes the fish like a bit drowsy. And the idea what we did is, okay, we calculate the exponents in the normal condition, and in this case where the fish are a bit drowsy, and we observe like the exponents, they change in the eptanol condition. And also, if we put stimuli to the larva and we want to decode, so we put stimuli to the larva and we decode the activity from the brain. Okay, so these are visual stimuli that can be in different places in the visual field, and we want to predict the location of the different stimuli just looking at the activity. So we did some decoding, and we observed that the decoding was better in the normal condition than in the case where we put eptanol in the bath. Okay, so a shift in the exponents is concomitant to a decrease of information processing. Okay. Okay, so these are just to show that neuronal avalanches can be related to behavior. Okay. Okay. So I would this would be the conclusions. Like you can infer models, these maximum entropy models, to characterize the state of the system you are observing. You can infer whether you have a phase transition between different states. You can separate the parameters into parameters that are very sensitive and parameters that are not very important for network activity. We show actually that the brain and cortical state transitions go along the stiff dimensions, whereas the stimulus-driven activity evolves along the slopy dimensions. Using renormalization group approach, we show that the fMRI activity scales and this scaling is a signature of criticality. And with neuronal avalanches, we show that, well, we have critical exponents in spontaneous activity. But if you perturb the system to deviate from criticality, you also perturb the information capability of the system. And so I would like to thank my collaborators and thank you for listening.